We're very happy today to have Greg Moore from Rutgers, and you can see his title here, N equals 2-star super Yang-Mills and Four-Manifold Invariants. Go ahead, Greg.
Thank you, Edward, for the invitation. So I'm going to be talking about a project I've been working on for a few years with Jan Manscott. And this is a progress report on that project. And it's closely related to work in these papers. You'll notice they date from the mid to late 1990s. And after I gave a talk on this project in the competing seminar, the one that competes with the Institute Monday seminar series, namely the Western Hemisphere Colloquium, last July, it was pointed out to me that there, just in the last few years, there's closely related work by several mathematicians. And I'll come back to that work at the end. It's quite interesting. So let me begin with some motivation. So let's begin by recalling the glorious history of the relationship between super Yang-Mills theory and four-manifold invariants. So the story begins with the discovery of instanton solutions of the self-dual Yang-Mills equations, 1975. And then in the hands of the Oxford School at Mathematics, that led to the discovery of Donaldson invariants in the early 1980s. And then Michael Atiyah asked some very perceptive questions, which were answered by Edward Witten. And he showed that the question was, how can you interpret the Donaldson invariants physically? And the answer is that they're correlation functions in a supersymmetric Yang-Mills theory. And in the process, Edward invented the concept of topological quantum field theory, although ironically, that example does not fit into what mathematicians understand as a topological quantum field theory. That's an interesting discussion for another time. Nevertheless, it started the subject. Now that was a very nice observation, but it formulated the Donaldson invariants as correlation functions in a strongly coupled quantum field theory. So it wasn't that useful for actually evaluating the Donaldson invariants. But all that changed in a dramatic way in the spring of 1994 when Seiberg and Witten did give an effective description of the low energy dynamics of these theories. And that in turn led to the discovery of Seiberg-Witten invariants in the fall of 1994, which in turn led to the revolution of 1995. And here I'm not talking about the string theory revolution of 1995. I'm talking about the revolution of four-manifold theory of 1995. And it was so dramatic that I think it left many physicists with the impression that all problems in four-manifold theory have been solved by the physicists. But that's really not the case. For example, a major outstanding problem is the smooth Poincare conjecture, which remains unresolved in 4 dimensions. And there's a host of other problems. I'll just mention one for fun. It won't play a role in the rest of the talk, but there's something called the 11/8 conjecture, which says that if X is smooth and spin, well, if X is smooth and spin, it's well known that the intersection form that calculates intersections of surfaces in this 4-dimensional manifold, the intersection form has to be of this form, some integer number m of copies of the E8 plus E8 lattice, plus some number of copies of the intersection form of S2 times S2. And then the conjecture says that n is bounded below by 3 times m, so it's saturated by connected sums of K3 surfaces. And there are many other open problems. So that in 2006, a leading expert in this subject, Ron Stern, wrote a paper with this title, and I don't know for sure, but I suspect that if he wrote a paper now, he might be still satisfied with this title. So the question is, can physics help with some of these open problems? So we don't really know, but the Seiberg-Witten revolution was based on pure SU2 n equals 2 supersymmetric Yang-Mills theory. On the other hand, the basic idea of topological twisting applies to any four-dimensional n equals 2 quantum field theory. So is there more to learn about four manifolds from supersymmetric quantum field theory? So that's the motivation. Now, indeed, we have learned more by studying other theories. So by including by including hypermultiplets in the simplest possible way, we discovered the superconformal simple type phenomenon. We don't know yet if physics will help with the big open questions, but it's worth a try. And certainly we'll learn many new things about supersymmetric quantum field theory along the way. So the way I like to think about it is getting there is half the fun. So that's the motivation. So now I want to say things about the setup, preliminaries, and background. So the four manifolds that we're going to consider are smooth, compact, oriented, and without boundary. And for simplicity, but certainly not for necessity, for simplicity, they'll be connected and simply connected. Now, we're also going to assume, as in Donaldson theory, that X admits an almost complex structure. And that's not actually a very stringent condition. It's really a simple topological condition. It means that the second Betti number, B2 plus, is odd. So B2 plus, if you introduce a metric, you can talk about self-dual degree 2 cohomology classes. And so B2 plus is the dimension of the self-dual degree 2 cohomology classes. Or if you think in terms of intersection theory, it's the maximal positive, the maximal dimension of positive subspaces of the second cohomology space. Importantly, we do not assume that X is spin because a lot of the fun questions have to do with non-spin manifolds. Let me say a word about what is an almost complex structure. So an almost complex structure means that if you allow yourself to multiply one forms by a complex number, or more formally, you consider the complexification of the cotangent bundle, then you can find locally a basis of one forms, EI, I running from 1 to 2, such that EI and EI star form a basis and transform across patches by action of a U2 matrix. And then there's a standard homomorphism of U2 into SO4, so that if you apply this, you get transition functions for the oriented cotangent bundle. Now, on a complex manifold, you can find holomorphic coordinates, Ci and Z, I bar, such that the EIs are proportional to the DZIs. But on an almost complex manifold, there are no ZIs, there are no DZIs, but there's still the EIs, so you could still talk about P comma Q forms. Let me give you a quick reminder about n equals 2 star supersymmetric Yang-Mills theory. So in the bosonic part of the Lie algebra of symmetries, there's an SU2 plus SU2 minus for local Lorentz transformations, an SU2R symmetry, and if it's a super Yang-Mills theory, there's a gauge symmetry. Now in n equals 2 star, the hypermultiplets are in the adjoint representation. So in our case, the hypermultiplet scalars will be in the adjoint representation of SU2 and made quaternionic. Now, we can right multiply on the quaternions by a unit quaternion. And so that's the action of the SU2R symmetry. So that means that if we assemble the quaternions into a doublet of two complex scalars, it's a doublet of SU2R. That's important because in topological twisting, we couple to a background SU2R gauge field. We do that in such a way that we can identify the SU2R symmetry with the SU2 plus in the local Lorentz algebra. And that means that our hypermultiplet scalar fields become spinners under topological twisting. So that raises the question, what if X is not spin? Well, in this case, you can cure the problem by introducing what I'll call an ultraviolet spin C structure. Ultraviolet because we need to introduce this spin C structure, a Gothic SUV, just in order to define the topologically twisted theory path integral in the ultraviolet. So now I'm going to take 3 slides and remind you of a few things about spin C structures. So first of all, the group spin C of 4 is pairs of 2x2 unitary matrices of equal determinant. And there's a homomorphism from spin C of 4 to SO4, which is very similar to the very standard and well-known one from spin 4 to SO4. So if you take a vector in R4 and you make it into a quaternion, then you can multiply on the left and the right by U1, U2 inverse. The phase cancels out because the determinants are equal. And so it's just like an SU2 action. So that defines an SO4 rotation. But the kernel of this homomorphism is U1. So by definition, to give a spin C structure is to give transition functions on your manifold valued in spin C of 4, so that if you apply this homomorphism, you get the SO4 transition functions of the cotangent bundle. Now, here again is spin C of 4, and it rather obviously has two-dimensional representations. I can take the fundamental of each of the 2 U2 factors. So then if I'm given a spin C structure, these define what we can call chiral spin bundles. I'll call them W plus and minus. And those bundles, they're rank 2 bundles. So if we take the determinant bundle, that could be a non-trivial complex line bundle. It has a first Chern class. That's called the characteristic class of the spin C structure. And with a little index theory, you can show that C squared minus twice the Euler character, or minus 3 times the signature, divided by 8 is an integer. And that integer will be very important to us. I'll call it L. Are there any questions at this point?
Actually, I have a question, Greg.
Yeah.
Basically, to introduce a spin C structure usually means that there's a U1 physical symmetry that you're using.
Yeah.
That must be one of the R symmetries, I assume.
No, it's a U1 baryon symmetry. It multiplies the hypermultiplets by phase.
It's a global symmetry of the
It's a global symmetry, absolutely. Correct.
Of a hypermultiplet.
Correct. Absolutely correct.
Okay, thank you.
Yeah. Now another little math fact is that an almost complex structure defines a canonical spin C structure. And the way that works is you can write a nice homomorphism, phi, from U2 into spin C4. So the first element is just the unitary matrix itself, and the second one is this funny unitary matrix with the same determinant as U. And then you can check that if you compose with the homomorphism to SO4, it's conjugate to the standard embedding of U2 into SO4. And for that canonical spin C structure, this integer L, which is important to us, is 0. So now the hypermultiplet scalars in the n equals 2 star theory are going to be spinners in the chiral spin bundle W plus. And it was understood, I think, by Labastida and Marino back in the 90s that you need a spin C structure to define the topologically twisted theory. But the detailed dependence on SUV has not previously been discussed, and for good reason, because including it turned out to be quite non-trivial. Now, there's an interesting lesson here. For n equals 2 star theory, you see the basic topological twisting of Witten needs to be supplemented with extra data. In this case, it's that spin C structure. And it's not known, at least not to me, how to twist the general 4-dimensional n equals 2 theory. So it's clear that you have to introduce extra data, and I understand it in some cases, but say for the general class S theory, I actually don't know how to topologically twist the theory. That's one interesting open problem. So now let's come to the topologically twisted partition function. So what data do we need to formulate the partition function? Well, this is a superconformal theory. So in the ultraviolet, there's a coupling constant. I'll call it the ultraviolet coupling constant, tau uv, and the complexified coupling constant is a point in the upper half plane. And the associated exponential of it is called QUV. And there's an n equals 2 preserving mass term, so there's a mass in the complex numbers, and it's not widely appreciated, but even in this superconformal theory, we need to introduce an ultraviolet scale lambda, and indeed, our topological correlation functions enter the theory only through the dimensionless ratio m over lambda. I'll call that T. As I've explained at length, we need an ultraviolet spin C structure, but it will only enter our correlation functions through the characteristic class of the spin C structure.
Sorry, Greg.
Yep.
Isn't this theory n equal to 4 super Young Mills in the UV?
Well, it depends what you mean. If you ignore the mass parameter, if you take the mass parameter to 0, then yes, it's n equals 4 super Young Mills.
But why do you need a UV scale? Maybe.
Basically because the mass, you can think of the mass as a la Zeiberg. You think of the mass as the vacuum expectation value of a weakly coupled U1. And that weakly coupled U1 is not superconformal. A more technical answer is that if you try and write down the prepotential, then there is actually, you'll find that you need to include, if you try and get the mass dependence of the prepotential really right, then you'll find that you actually need to introduce this UV scale. Now, Juan, notice that m equals 0, which gives you the n equals 4 super Young Mills theory, then the lambda doesn't matter anymore. So maybe that'll make you feel better. Is that okay? No?
Okay, I didn't understand why you need.
You didn't understand what I said?
No. I think I understood what you said, but
Okay.
I thought you would tell me there is maybe some diversions, some new diversions that.
And unlike Juan, I didn't understand your answer to Juan's question, so I would appreciate it.
Okay, this is bad. Okay, I don't want to take too much time on this. I'm pretty confident about this. So again, what is this mass? Think of the mass as a VEV of a weakly coupled U1. So I'm sure Nadia understands that. Now, you need to think of it this way in order to get the correct mass dependence of the prepotential. But if you've got a weakly coupled U1, then that is not superconformal. So there are terms in the prepotential.
No, it's weakly coupled in the limit that its coupling constant goes to 0.
Well, that's the definition of weakly coupled, yes.
Well, but in that limit, it don't need to introduce that scale.
No, not true. There's a log of m squared over lambda squared. And
charge fields under
it
this.
will also appear in the Nekrasov derivation of the prepotential. We went through that extremely carefully with Xinyu Zhang. And there, maybe one will feel better because there is a kind of divergence at one loop that needs to, you need this lambda. And look, the mass parameter, I'm going to be writing down topological correlation functions, so they better not be dimensionless.
I guess the hypermultiplet is charged under this U1, right?
Yes, exactly. Yes, exactly. Yes. So let's not get hung up on this. If you don't like lambda, set it to 1, okay? So, and then the last piece of data. So I'm writing down the data that you need for the topological partition function, and they will be functions of t. If you don't like what I said about lambda, just substitute m for t. And the last piece of data I need is the 't Hooft flux, because the SU2 theory partition function will have an 't Hooft flux. Okay. Now, of course, if we're going to write the Lagrangian in the path integral, then you also need to introduce a metric, but the energy momentum tensor is Q exact. So the metric dependence should drop out. And in the same vein, the action for this theory is not only metric independent, it's holomorphic in tau uv up to q exact terms. So we also expect z should be holomorphic in tau uv. This theory also has q-closed operators. So we have operators associated with points. If phi is the vector multiplet scalar field, so it's adjoint valued, we can insert that at points. We can sum over points. If we have a surface, we can integrate over the surface of trace of phi times f. These turn out to be q-closed. And not only that, the q-cohomology class of these things only depends on the homology of your sum of points or your surface. So the path integral defines a function that depends on the four parameters, nu, tau uv, cuv, and t, from the homology into the complex numbers, and it's just the correlation function of e to the O of x, where x is the homology class, O of x is the corresponding operator. We look at the generator of its correlators. And so this is the function that Jan and I evaluated very explicitly and used it to check some physical expectations. So now I'm going to go over the main physical expectations and the main lessons that we learned from the explicit results. Are there any further questions? We can come back to the lambda later. Okay, so first, in their paper, Zyberg and Witten showed that the Zyberg-Witten curve for n equals 2 star is invariant under S-duality. So what about the partition functions? Well, the partition functions are indeed suitably S-duality covariant with some interesting non-trivial details, which I don't think have appeared in the literature previously. But I've talked about that a lot in previous talks on this project, so I'm gonna skip over that. Now the second one is, well, Zyberg and Witten also noted that, unsurprisingly, as the mass parameter goes to infinity, the hypermultiplets decouple and you get the pure super Yang-Mills Zyberg-Witten curve. Technically, you take QUV times m to the fourth, you set that equal to lambda naught to the fourth, where lambda naught is some fixed scale, take m to infinity and q to 0. And so the question is, does the limit of our partition function exist and give the Donaldson-Witten partition function? The Donaldson-Witten partition function is the generator of the generator of Donaldson invariants that comes from the pure theory. And the answer is yes, sort of. The limit actually does not exist, but z nu is actually a sum. Well, when b2 plus is bigger than 1, z nu is naturally a sum of 3 terms. You have to throw one of them away in a natural way and renormalize the other two, and then there's a well-defined limit, and it reproduces the Donaldson-Witten function with an interesting orientation issue that we won't get into, related to 't Hooft anomalies of one-form symmetries in modern language. Now, the third question.
Is the one that you throw away, is that the one where SQ2 is Higgs? Because phi has a Vev?
Yes.
Thank you.
It's the, at large mass, it's the one at weak coupling. Right? We're talking about the same thing?
Yes.
Yeah, okay. Yeah, that one. Okay, so now, as I mentioned before, the action is of this form. So the natural question is, is the partition function metric independent and holomorphic in tau? And the answer is yes, when b2 plus is bigger than 1, and absolutely not when b2 plus is equal to 1. In fact, most correlators vary continuously with the metric. So if you look at a correlation function like this, with fixed r and n, it varies continuously with the metric when n plus r over 2 is sufficiently large. In other words, it's bounded if it's larger than this integer L that I defined before. Which means all but finitely many correlators are actually not topological, but we can derive very explicit formulae for the holomorphic and metric anomalies, so we understand very well how it depends on metric. I should say something very similar was observed by Edward and me in the NF equals 4 case also. Now, again, using Q symmetry, the couplings to the background spin C connection is expected to be holomorphic in the coordinate on the Coulomb branch, usually denoted U. So you take the trace of the adjoint scalar squared, you take its vacuum expectation value in a vacuum on the Coulomb branch, call that U. And going back to Shapir and Tachikawa, we expect that the low energy effective theory should have holomorphic couplings, kappa 1 and kappa 2, where capital F sub S is the background spin C connection and little f is the dynamical U1 field strength on the Coulomb branch, low energy effective theory. And here I'm using Zeiberg's convention of small letters for dynamical and capital for background. Okay, the answer is yes, kappa 2 is holomorphic. No, kappa 1 is not holomorphic. And at least for me, personally, this is a huge big deal. So let me stress this. So I think an important physical principle is that the measure on the Coulomb branch is physical and should be single valued. The Coulomb branch is physical, and I think the Coulomb branch measure should also be physical. And you shouldn't have to go to something like a finite cover of the Coulomb branch to get a good measure. And this is highly non-trivial because several of the couplings in the low energy effective theory are multi-valued. In fact, there's not even a global duality frame. There's not even a global notion of what is the photon. So it turns out that with holomorphic couplings, there's no single valued measure. So it's a kind of anomaly. I don't know how to phrase it in terms of the standard theory of anomalies, but to me, it's a kind of anomaly. As I'll explain later, this has important implications for the class S generalization of these results. And by the way, we also give very explicit formulae for these couplings, which are non-trivial. Finally, the m to 0 limit should be some kind of topologically twisted partition function of n equals 4 super Yang-Mills. So what do we get? Well, the t, or mass dependence, turns out to look like this. There's an overall factor of t to the minus 3L times a function z tilde, which has a good t goes to 0 limit. So it's going to blow up or go to 0 unless little l is equal to 0. So a non-trivial limit only exists when the spin C structures are determined by an almost complex structure. And in cases where we can compare, such as projective surfaces, the limit does indeed reproduce the Waffle-Witten invariance. Why Waffle-Witten? Why should Waffle-Witten have anything to do with it? Well, as m goes to 0, as we just discussed, we get n equals 4 super Yang-Mills. Waffle-Witten is the renowned topological twisted partition function of super Yang-Mills theory. But this is actually a little surprising because the Donaldson-Witten and the Waffle-Witten twists are very different. And moreover, contrary to what I said in the competing seminar in July, the Q fixed point equations are actually different in general. I'll come back to that point.
Greg, before
Yeah.
you go, concerning the anomaly,
Hmm?
you left us hanging a little bit. You said that some couplings aren't holomorphic.
Yeah.
Divided or whatever.
Yeah.
But I guess the physical things are in the end. So I assume that the coupling.
Well, I'm talking about holomorphy in U.
Yes, I just said that. But
Okay. Well, the measure involves du bar. The measure is not holomorphic at all. But I would have expected, and for a long time, I expected that these couplings would be holomorphic.
okay, but is there something you're going to tell us that explains why they're not? Is it because there's some?
I'm going to show you what I believe are the correct couplings.
Okay.
And again, the best way to think of it is think of the mass as the vacuum expectation value of a weakly coupled U1.
Yes.
So if you think of it that way, then you write the action for a higher rank low energy effective theory.
Yes.
U1 times U1. One is the dynamical U1 on the Coulomb branch. The other is the U1B, the U1 baryon number.
Mm-hmm.
And then, as you know, you have tau bar times f plus I, f plus, you have tau ij, f plus I, f plus j, plus tau bar ij, f minus I, f minus j. And so that's basically my explanation of why it's natural that this is not holomorphic.
Okay, thanks.
But before I had thought about it that way, Jan and I were going crazy trying to write down a holomorphic kappa such that the measure would be single valued. And we kept missing by eighth roots of unity.
I'm confused by something here.
Yeah. Mm-hmm.
The object that is not holomorphic, does it have to be holomorphic if we assume supersymmetry?
Well, it's the usual Q symmetry arguments suggest that it should be holomorphic.
If I did not do any twist, I just took the theory without the twist, is there a corresponding coupling in the theory?
Sure.
And is that holomorphic?
Sure. This F sub S is just some background spin C connection.
So it involves gravity or not? Is it a question in rigid supersymmetry? Does it involve curved
This is a
space or
question,
not?
Nadi, this is a question about the low energy effective action when I'm coupling to external gauge fields.
So just by rigid supersymmetry, you say it has to be holomorphic. You don't need supergravity.
I didn't say that.
I'm asking. This is a question.
No, I don't think that's true because I think we have a supersymmetric low energy effective action, which is not holomorphic. And let me repeat what the answer is. And I mean, unfortunately, I don't have an iPad to write equations, but let me say it in words. You know that if you have a higher rank theory, that you don't have a tau, you have a tau ij. And you don't have a single photon, you have a multiplet of photons. It's called an F upper I. So you shouldn't be surprised that you have a kind of effective action like tau lower ij, F plus upper I wedge F plus upper j, plus tau bar lower ij, F minus upper I wedge F minus upper j. I'm saying that's exactly what we have here once you realize that mass, once you realize that this F is the field strength for this U1 baryon. I'm writing down the effective action for U1
Greg,
cross
whatever
U1
it is,
theory.
it should come from a prepotential.
It does.
Holomorphic. And
Yes,
the prepotential should better be holomorphic.
Okay, you guys are getting upset about exactly the same problem. This prepotential is really the prepotential for an SU2 times weakly coupled U1 theory.
And that one is holomorphic.
Well, of course, the prepotential is holomorphic.
Okay. So what is not a holomorphic?
This coupling in the effective action is not holomorphic.
Maddie, I think we're being told that the puzzle gets resolved by writing it in terms of prepotential.
Yeah, unfortunately, I forgot to put the timer on my clicker, so I think I'm running out of time. So why don't you harass me about this after the talk?
Okay, with pleasure.
All right. So I want to say something about more precise mathematical formulation of the partition function. So what does it look like to a mathematician? So we start with a principal SO3 bundle, and our fields are a connection on the SO3 bundle, and I'll call it a monopole field, which is chiral spinor valued in the, which is adjoint valued and complex. And so then the Q fixed point equations look like this. So these are these are the non-abelian versions of the Seiberg-Witten equations. They're called the non-abelian monopole equations. And so if we fix a second Stiefel-Whitney class and a 't Hooft flux and an instanton number, then we have a well-defined moduli space of solutions to these monopole equations. And so now mathematically, our partition function is a sum over non-negative instanton numbers of q to the k with certain integrals over these moduli spaces of e to the mu of x. So mu of x is a map from the homology of the four-manifold to the cohomology of the moduli space. It's an analog of the famous Donaldson mu map. And then an Euler character, or actually an equivariant Euler character of a bundle associated to those differential equations. And so then the standard argument for why this is true is that the path integral has a Q symmetry. So the path integral is an infinite dimensional tome class, which localizes onto this finite dimensional moduli space of solutions of the monopole equations. So I want to say a little word about this moduli space. So if you calculate the virtual dimension of the moduli space, it's 2 times our integer L times the dimension of the gauge group, 3 in our case. And I want to stress that it's independent of instanton number K. And that's kind of funny because the moduli space of instantons goes like 8K, but the index of the Dirac operator goes like minus 8K, so the K dependence cancels out. And that's very important because it means that correlation functions for any given insertion of an operator, even the partition function itself with no operators, becomes an infinite series in QUV. There's no ghost number anomaly that in Donaldson theory picks out a particular instanton number for any given insertion of operators. It's very unlike that. And that's, of course, important for S-duality and modular invariance. These symmetries also, these equations also have an important U1 symmetry where I rotate the monopole field by a phase. So this U1 acts on the moduli space, and this mu of x is actually in the equivariant cohomology, and it's the mathematical counterpart of the physical operator O of x, and the physical parameter m over lambda is the equivariant parameter, the U1 equivariant parameter. So if we localize with using that U1 symmetry, then we look for the fixed point set under rescaling the monopole field by a phase, and there are actually 2 branches. First of all, clearly if I put the monopole field to 0, that's a fixed point. And if I put m to 0, I get the instanton equation. So inside this moduli space, MQK is the moduli space of instantons. So that's one branch of fixed points. But we can also have another branch where the monopole field is non-zero, but upper or lower triangular, and then multiplying by a phase is equivalent to a gauge transformation. So that's also a fixed point. And we'll call that the abelian branch because the equations boil down to abelian Seiberg-Witten equations on that branch.
Greg, in that last statement, that's a fixed point, you assumed that the gauge field was diagonal, I think.
Yes. You have to have a reducible connection. That's right. Absolutely. Well, that's part of the statement. That's why we call it abelian, the abelian branch.
Okay.
Yeah. So, so the U1 localization looks like this. You have a sum over the instanton and the abelian branch. And let's first focus on the instanton contribution. Then we can take, it's interesting to look at the mass to 0 and infinity limits here. So this equivariant Euler class we can write out as a product over the splitting classes and write that as a polynomial in T, which I've written this way to pick out the various Chern classes. So now it's nice to observe that if the mass goes to infinity, then clearly the leading term is the 0th Chern class, which is just 1. So if I replace the Euler class by 1, well, I get e to the mu of x, and lo and behold, that's the definition of the Donaldson invariance a la Donaldson. So on the other hand, if I take m to 0, then I get the top Chern class. And if I take the spin C structure determined by an almost complex structure, then this bundle E is the cotangent bundle of moduli space. So if I take m to 0, I should get something like the Euler character of the instanton moduli space. Now, famously, the Waffle-Witten invariants compute the Euler character of the instanton moduli space. And moreover, they're S-duality covariant. So it's natural to guess that we get the Waffle-Witten invariants. But as I said before, that's kind of odd because the Waffle-Witten twist of n equals 4 super Yang-Mills is different from the Donaldson-Witten twist. And let's just look at the Waffle-Witten equations. So what are the fields in the Waffle-Witten equations? We have a connection on the principal SO3 bundle. We have an adjoint valued scalar field C and an adjoint valued self-dual 2 form B. And then here are the equations. And they don't look very much like the Seiberg-Witten equations. But it helps a lot to use the almost complex structure, because then we can introduce a form called the almost Kähler form, which is like a Kähler form, but it's not closed. And then you can write the general self-dual 2 form as a scalar field little b times omega plus the real part of a 2-0 form. Remember, if you have an almost complex structure, you can talk about PQ forms. So then if you add in the scalar, there's a complex structure on the space of fields, and holomorphic coordinates are C plus IB and beta 2-0, which I've suggestively put into a doublet. As I explained before, an almost complex structure also determines a canonical spin C structure. And if you look at this diagonal matrix 1.u, you see that the pullback of the chiral spin bundle is the trivial bundle plus the 2-0 forms. So it makes sense to identify the Vafa-Witten and the Seiberg-Witten fields this way. And indeed, if you do that translation, the first of the Seiberg-Witten equations becomes the first of the Vafa-Witten equations. But the second equation is more troublesome. The second Vafa-Witten equation looks like this. And if you put it into this language, the second Seiberg-Witten equation looks like this. So contrary to what I said this summer, Seiberg is not the same as Vafa. I really ought to have known better. But they're pretty close. The difference of this connection on B with D star is a 0th order in derivatives and a tensorial. So, it's easy to make a mistake here. So almost complex geometry is almost impossible to understand, largely because of the 9-house tensor, which is almost impossible to pronounce. Anyway, the topological invariants appear to be the same. So our conjecture is that the moduli spaces are in some sense equivalent. And that's actually quite an important remark, if true, because ever since the Vafa-Witten equations were introduced, we've been bedeviled by the non-compact branches where B and C are turned on. But if we have this equivalence to the adjoint Seiberg-Witten equations, then they have an SO2 symmetry, and working equivariantly with respect to that SO2 symmetry we might be able to tame the non-compact branches. So that's a subject for the future. I should say that for projective surfaces, in recent years, mathematicians Tanaka Thomas and Golompur Shishmani Yao gave precise mathematical definitions of the Vafa-Witten invariants, but they used very heavy-duty algebraic geometry, and those techniques will not generalize to the more general four-manifolds we're talking about. Okay, so I've got about 15 minutes. So I just want to say a little bit about how we get these explicit results. And I'm going to have to go lightly because I don't have much time left. So you see, the story starts with what's called the Coulomb branch integral. So the partition function on a compact manifold will be equal to a sum over all the vacua. In particular, we need to integrate over the Coulomb branch of vacua. So we'll have an integral, and it turns out to have this form. B is the Coulomb branch. So H is some holomorphic metric independent function, which we know all about, but I'm not going to tell you about. And psi is a non-holomorphic metric dependent theta function-like object, which I will tell you a little bit about. So today the Coulomb branch is just the complex numbers, but the generalization to class S is not known, but should be interesting. So what did Seiberg and Witten do? They said that we can understand the low energy dynamics by writing down a family of elliptic curves. So think of them as C mod Z plus tau of u z. So tau is holomorphically varying with u. And generically, they're smooth elliptic curves, but at 3 points, they degenerate. Now, remarkably, you can invert this tau as a function of u to write u as a function of tau explicitly in terms of theta functions. We don't need to know the explicit formula, but the end result is that the Coulomb branch can be identified with the modular curve for the congruence group gamma of 2. So let's choose the fundamental domain for gamma of 2, like this one here. And then the 3 points where the elliptic curve degenerates are tau goes to I infinity, tau goes to 0, and tau goes to 1. Our measure will be singular at those points, and it will also be singular at tau uv. So we want to integrate over this pink region. So our measure looks a little like this, and I want to talk a little bit about this psi function. So to 0th order, it's just the partition function of the low energy Maxwell theory. So it's the sum over the topologically inequivalent fluxes of e to the minus Yang-Mills Maxwell action. So it's frame dependent. You have to choose a photon. It's not holomorphic. It's metric dependent, but it's not very metric dependent. The metric dependence is entirely through something called the period point. What's the period point? Well, if B2 plus is bigger than 1, the Coulomb branch integral is 0. We don't need to worry about this. But if B2 plus is equal to 1, that's when it's non-zero. And then when B2 plus is equal to 1, the second cohomology space is Lorentzian. And so there's a unique cohomology class, degree 2 cohomology class J, which lives in the forward light cone, is norm square 1, and is self-dual. So the Hodge dual depends on the metric, and therefore J depends on the metric, but that all the metric dependence comes through J. Now using J, you can write down self-dual and anti-self-dual projections of the dynamical field strength. So a better approximation to the psi function is this one here, where you're summing over fluxes, or more precisely, you're summing over first Chern classes of the low energy photon line bundle. Here's a more precise formula. The capital E is a function I'm not going to tell you too much about. It's some kind of error function. The important thing is that all the metric dependence and non-holomorphy is in E, and it's a total derivative. It's naturally, in a very natural way, it's a total derivative with respect to tau bar. The rest is holomorphic and metric independent. Lambda is the first Chern class of the dynamical photon. Z is CUV for the background spin C structure times a function V, which I'll tell you more about on the next slide. So lambda dot Z is a coupling of the low energy photon to the background spin C connection. And if you write it out in full glory, this is partially an answer to the question that Nadi was asking me about before. Here's the coupling of the background spin C structure to the dynamical photon. As I was stressing, it violates some folklore. And what is V? V is the second derivative of the prepotential with respect to A and M. So again, to address questions that I was being asked about before, you'd better know the right M dependence of your prepotential to write this down. You can write this down in terms of special Kähler coordinates, and Jan discovered a remarkable identity for this V. If you consider the ratio of these theta functions and insert V and tau, 2 tau precisely, then that actually is independent of where you are on the Coulomb branch. It's, if you like, a renormalization group invariant. So it's constant. That turns out to be a very useful fact when proving that our Coulomb branch measure is single valued. As I mentioned before, this coupling has important implications for class S. So if you take the mass goes to infinity limit of this coupling, then the V goes to a constant. And so what happens is you recover a plus or minus sign, that's all. And in fact, it's the famous plus or minus sign, the famous sign that Witten introduced in his paper on abelian S-duality to explain S-duality of just Maxwell theory. From the 6-dimensional point of view, it comes from a Z2 valued quadratic refinement of the intersection form that's used in defining the self-dual 2 form in 6 dimensions. But we see here that actually in the n equals 2 star case, which of course should also come from 6 dimensions, we're getting something that's actually C star valued. So that means that the 2-0 theory, I suspect that the correct quadratic refinement of the intersection form for the 2-0 theory should involve a U1 valued quadratic refinement. Okay. Very little time, so let me just tell you few quick things about how you actually evaluate the Coulomb branch integral using Mach this and that. So I hope you'll believe me that the Coulomb branch integral boils down to a sum of a bunch of integrals of this form. You're integrating over the fundamental domain of SL2Z of some power of the imaginary part of tau times a series, which is explicitly known and has a nice Q and Q bar expansion. Can have negative powers in Q and Q bar, but it's bounded below. And how are you going to do this integral? Well, a good way to try and do the integral is to try and do it by integration by parts. So you try to write the integral, m tau to the minus s f as a total derivative with respect to tau bar, some h hat, and then you're left with an integral over the boundary, the blue boundary region here. And that's pretty useless unless the h hat is modular. But if the h hat is modular, then the finite boundary contributions will actually cancel thanks to modular invariance, and you're left with an integral across the fundamental domain from -1/2 to 1/2 at large m tau, and you take the limit to infinity. Now so it looks like it's no big deal, right? So you just got to solve that first order differential equation. Okay, now this is really just an exercise in first year calculus. You can find a function r which is vanishing exponentially fast and solves this first order differential equation. There's no big deal here. You can just write it down explicitly in terms of indefinite gamma functions. But then what happens is that r is not modular. On the other hand, the differential equation is modular. So the failure of r to be modular, it better be some holomorphic shift. So that suggests that there's a holomorphic function h of tau such that h of tau plus r is modular. And such an h of tau is what's meant by a Mach modular form. Everything has a nice Fourier expansion here. So h of tau will have a nice Fourier expansion. So if you can find h of tau, you're home free. You write the integrand as a total derivative. As I just explained, all of the finite boundaries cancel. You're just left with the boundary region at infinity, and that gives you the constant term in the Q expansion of the Mach modular form. Now notice that it's undetermined by the differential equation fixed by modular invariance, so it's slightly subtle. But it's all pretty elementary. So that's the technique that we use to evaluate the Coulomb branch integral. We write the measure as d of a one form. Our one form had better be well-defined, no monodramy or anything like that. It better be non-singular, away from the points where we know there's going to be trouble. And it better have a good Q expansion near the cusps. And these conditions determine this G hat uniquely as a modular completion of what's called an Appel-Lerch sum. This h of tau does not look very modular, but remarkably it has a modular completion, non-holomorphic modular completion. And it also looks like it has lots of nasty poles in the Z, and it does, and that turned out to be a major technical headache, but rather magically, because of that identity of Jan's that I showed you before, the bad things from the poles actually go away. Anyway, for the ultraviolet spin C structure determined by an almost complex structure, we find expressions that look like this, where G nu is the famous kind of Mach modular form that we learned about from Zagier, and thus we reproduce results of Waffe and Witten. But we can also generalize to other spin C structures. So for CP2, we get other kinds of holomorphic anomalies. And we can also introduce operators. So for CP2, here's the result where I've introduced various powers labeled by n of the point operator. So if I don't introduce any powers of the point operator, I just have the partition function itself. That's the first line. And that indeed is the Waffe-Witten answer. On the other hand, I have all the rest of the thing, this table where I do insert various powers of the point operator. And if I keep the terms that survive the m goes to infinity limit, then I get the Donaldson invariance for the point operator on CP2. So the green are the Waffe-Witten invariants, and the red are the Donaldson invariants, and the rest is some generalization. All right, so 5-6 minutes. I want to say a few things about the low energy effective theory near the cusps and what our explicit results look like. So as we learned from the Zyberg-Witten paper, near each of these three cusps where the elliptic curve degenerates, the description of the vacuum changes. We instead have a U1 vector multiplet coupled to a charge 1 hypermultiplet in a suitable duality frame. And there's a separate contribution to the path integral coming from the path integral of each of these three low energy effective theories. We add up all the contributions because as I said before, we sum over vacua. So that's the general form of the partition function, the Coulomb branch integral that we've discussed so far, and then a contribution from the three low energy effective theories valid near the three cusps. And in fact, when B2 plus is bigger than 1, the Coulomb branch integral vanishes from fermion zero modes, and all we get are the contributions from the three cusps. And those are true topological invariants. So of course, it's quite interesting to determine what these are. So we're trying now to talk about the low energy effective theory, which is valued in these small red regions of the Coulomb branch. Now near these cusps, we can introduce a local special Kähler coordinate, and our effective action will be a sum of a bunch of couplings, little f n, multiplied by little delta n, where little delta n are the possible local topological densities, and that's true up to some Q exact stuff. So if I know the fn's, then when I evaluate this, the partition function of this low energy effective theory, by say localization, I'll set a to 0, and the exponential of little f is big F, and the topological invariant associated to little delta n is big delta n, big delta n. So what are the possible topological couplings we have to worry about? Well, because we have a four-manifold, we have the Euler character in the signature, and that leads to the famous A to the chi and B to the sigma couplings that were introduced by Witten. But now we have this ultraviolet spin C structure and a tuft flux, and so we have some more couplings to worry about. And then the low energy effective theory has a photon, so it has a first turn class. I'll call it the infrared C. It's actually a spin C structure, so it's the infrared spin C structure, not to be confused with the ultraviolet one. So there are some more couplings. And then if we include observables, there are 4 more couplings to worry about. So altogether, the contribution at the cusp J is a sum over the U1 photon topological class, the C infrared, of the Zyberg-Witten invariant of C infrared, that's an integer, times the product over these 12 couplings.
Sorry, why are the UV and the IR spin C structures not the same?
Why should they be the same? I introduced an ultraviolet spin C structure just to get off the ground, just to define the theory in the UV. But you know, we're summing over all the vacuum solutions, so we have to sum over all the topological sectors of the U1 photon in the infrared. I mean, this sum over C infrared is just like the sum over the first turn classes of the low energy U1 photon in that theta function I talked about before. Right, I'm evaluating a partition function. I have to sum over all the contributions of all the different topological sectors of the infrared fields.
Does CIR depend on dynamical fields or only classical vacuum?
CIR, so in the infrared, as you taught me, there's a dynamical photon, right? Right. Also in the theory, which is valid in the neighborhood of the point uj. So there's a photon there, and U1 theory, and it has a first turn class. It's really a spin C connection, but loosely speaking, we can think of it as a U1 gauge field, and it has a first turn class. And we should sum over all over the field, over all the topological sectors of the information.
Oh, I see why I was confused. Thank you.
Okay. Okay, good. So, okay, so we sum over that. I should say that, well, okay, maybe okay. There's a renowned formula for the Donaldson invariance in terms of the Seiberg-Witten invariance, which Edward wrote, which in mathematics is called the Witten conjecture. And it involves something very similar to this, where you have a sum over CIR over CIR. Okay, I'm going to ignore that chat because I'm running low on time. So you have a sum over CIR, and instead of this product over these 12 functions, you have some simple trigonometric expressions. Well, I don't have time to really do a careful comparison. So this is the kind of thing you get, and now how do you get these? How do you get these couplings? How do you get these couplings in the low energy effective action? These little FNJs. Well, there's a trick, I think an underappreciated trick, that Edward and I used in our paper from 1997, where you can get these couplings by using the wall crossing behavior of the Coulomb branch integral at uj. So the basic principle is that the metric dependence should only arise from the boundary contribution at u goes to infinity. And if you buy that, then you see there's some metric dependence, some variation of the Coulomb branch integral coming from singularities at uj. And when B2 plus is 1, there's also metric dependence from the Seiberg-Witten contribution. But those two things should balance each other. And this turns out to be a very strong condition. It's strong enough to determine all 12 couplings. So to summarize, your partition function looks like this. Each contribution of each cusp looks like this. And here is what the results really look like. So in the boxed equation at the top, I show you the contribution from the cusp at U1. And the main thing to get from this is that I'm writing various modular functions raised to the power, and the powers are various topological invariants. The boxed equation on the top has no insertions of observables. If I include, for example, the surface observable, then I have in the exponential s.cir times various modular functions, which are listed in the second table, or s squared times various modular functions, or s.cuv times various modular functions. So that's what the results look like. So now, I'm over time. Okay, so
About a few minutes, Greg.
I can take a few minutes. Okay, so let me say real quick something about relation to other people's work. So for the canonical spin C structure determined by an almost complex structure and the mass goes to 0, we recover and generalize formulae from the Vafa-Witten paper and also from a nice paper of Dycroft, Park, and Schruers for the Vafa-Witten invariants. When CUV is 0 and our manifold is spin, we recover formulae that were written in by Labastida-Lozano. As I mentioned before, in the m goes to infinity limit, we recover the Witten conjecture after suitable renormalization and fudging. Fudging in the sense that you have to throw away the contribution from the cusp U1. The discussion on Mach modular forms generalizes and, to my mind, explains much more systematically some observations about relations of the U-plane integral in special cases to Mach modular forms from the 90s. And so it's a generalization and unification of these results from the 90s, but more recently, in the last year, there have been some physical derivations of the holomorphic anomaly in the Vafa-Witten theory by these two papers. So ours is an independent derivation of the holomorphic anomaly. And as I mentioned at the beginning, there's been some parallel work, which we were until recently completely unaware of, by mathematicians, Goethe, Kuhl, Nakajima, and Williams. And it's very interesting to compare with their results. So On the one hand, we're talking about general four manifolds. They're talking about projective algebraic surfaces. They use heavy-duty algebraic geometry. They use this Mochizuki theory. We have an arbitrary spin C structure. They have the canonical spin C structure determined by the complex structure. But when we can compare, remarkably, as you saw, these formulas are actually quite complex, and they're bang on, absolutely the same. It's pretty amazing. Moreover, the mathematicians did something we didn't do, which is they gave a further refinement of the invariance by computing the chi-y genus of the moduli space of sheaves. And it would be very interesting to see how to do that from the physics point of view, especially since the result involves infinite products, which are nowadays called, well, they're related to things that Zagier has called quantum modular forms. So the other thing that comparing with their results shows is that the instanton contribution can be identified with the results at the cusps U2 and U3 and the abelian contribution from U1. So the instanton contribution alone cannot be S-duality covariant. Okay, so let me conclude. So I already said this. This next statement is unfortunately a time translation invariant statement. The Hamiltonian formulation of these theories should be a very interesting thing to understand better. And as I've said several times during the talk, the six-dimensional point of view in the generalization to class S ought to be very interesting. And finally, as I just mentioned, when X is complex, there are these very interesting refined versions, and it would be quite interesting to get those from physics. So that concludes the talk. Thank you.
Thank you, Greg. So let me turn it open for questions. I had one, this chi-y generalization that you mentioned.
Yeah.
Is it something that has a path integral realization in 4 dimensions? Or would you try
That's part of my question. Yeah, I have some thoughts. I've discussed that with Jan a bit, but nothing concrete. It's, you get things like the McMahon function where you have a products of 1 minus q to the n to the n. And even worse, you get products of 1 minus q to the n squared. So it would be very interesting to reproduce that either from a path integral or maybe from BPS counting functions.
But I wonder if they'd be BPS counting functions in 4+1 dimensions.
Something like BPS counting functions in 4+1 dimensions, right? Yeah, I mean, they're a little reminiscent of these infinite products that you get from the halo picture of BPS states. But again, that's a 4-dimensional picture. Yeah, I really don't know. I think I mention it because I don't know. It's an interesting open problem.
Anyone else with questions?
Yeah, I'd like to still understand this anomaly, this holomorphic anomaly better. So,
okay.
Is it present also in local quantities or only when you integrate over the U-plane?
No, it's local. I mean, depends what you mean by local. I think of the measure, the Coulomb branch measure is a local thing. Here we go.
But
Here's
then
the
I'm
anomaly.
really puzzled. If I think of it on R, put the theory on R4, I think of it as rigid supersymmetry with some background gauge fields. Is there anything? Are you saying that the prepotential is not holomorphic or not?
Yeah, Nadia, I don't really understand why you're bothered by this. You're not bothered by the fact that tau and tau bar enter non-holomorphically.
That's correct.
It's the same thing.
But the prepotential is holomorphic.
Absolutely. So you didn't bother me when I wrote this formula for the Maxwell theory, right? With tau bar of u and
this
tau.
This doesn't bother me.
That doesn't bother you. Well, the other one shouldn't bother you either, because it's just tau ij. It's just a tau matrix.
But then I'm not surprised if it's not holomorphic.
Well, okay. I mean,
I thought that what used to be holomorphic is
in
the
hindsight, it's obvious when you fall off a roof that there's no gravity. I mean, you can't,
no, but the question is
yes, yes. In
not an
hindsight, it's
anomaly.
obvious. In hindsight, it's
no.
totally obvious. Yes, I agree. Okay, I'm sorry I said it in such an obscure way. I said it. I mean, I was really, we were really going crazy because we thought, you know, there are these Q symmetry arguments that said that these couplings had to be holomorphic. And then we were saying, okay, well, what possible holomorphic function could we put there that made the measure single valued? And the answer was, well, we couldn't find one. And then we said, oh my God, wait a second. Let's think about it a la Zyberg and Nelson thinking about a background VEV and a weakly coupled U1. And then, as you say, it became obvious.
Okay.
That's why you say, look, Nadi,
Okay,
look at the formula. Let me make it more obvious. Look at the formula for V. It's the second derivative of F with respect to A and M, right?
There's no reason for this object to be holomorphic. I thought you were surprised because it
There
was
is, well, okay. Very, very, very smart people said it would be holomorphic, and very dumb people like me believed them. And for 2 years tried to find a holomorphic function to make the measure work. Okay. And moreover, I mean, so this, you know, and as I say, the fact that this coupling is not holomorphic means that the generalization of Witten's phase here is non-trivial. So I think that's going to be an important aspect of the generalization to class S theories.
Are there any, sorry about the phone ringing in the background here. Are there any other questions?
I was wondering if you could say something about floor theory that you mentioned on your very last slide.
Unfortunately, it's a great question, and unfortunately, I can say very little about it.
Mm-hmm.
But I do want to make a remark here about just an amazing historical irony, which is if you go back to Edwards' paper, where he introduced topological field theory, it's very interesting to see how he starts, the chain of logic he uses. He starts with floor theory.
Mm-hmm.
He starts by saying there's floor theory, and then he writes down a Hamiltonian for a quantum field theory, which should give you this floor theory. And then he says, oh my God, this Hamiltonian is the Hamiltonian of a topologically twisted n equals 2 supersymmetric Yang-Mills theory. Mm-hmm. And the reason it's such an irony is that this is at the heart of the reason that this is actually not technically a topological quantum field theory, because you can't define it on all four manifolds. Well, there are technical problems with defining floor theory on general three manifolds, like the three sphere. So, you know, this is a topic where there's been a great deal of activity in the mathematics community, and now there's a huge number of versions of floor theory. But I think it would be a good thing for the physicists to revisit this, because they might bring some new insights. But
right. So
more than that, I really can't tell you anything more.
Okay. Well, yeah. So that's what I was wondering. I mean, there's like many versions of floor theories. So
oh yeah.
In particular, I think
this is what's called instanton floor theory.
Well, I mean, what I would think that what you're talking about is that maybe there's an equivariant generalization of monopole floor theory, because you described the low energy.
Oh, absolutely, there is.
I see.
I even think it was discussed at the Park City Institute,
Right.
2 years ago. They had a lot of talks, if you remember, they had a lot of talks about floor theory, including certainly equivariant monopole floor
Well,
theory was
so,
mentioned.
well, I'm not sure if they discussed exactly what you're talking about, which is where
Well,
I'm thinking,
not this particular theory. Yes, that's why I'm listing it as an open problem. Yes,
yeah.
mathematicians, with one significant exception, mathematicians never pay attention to the generalizations with hypermultiplets. The significant exception is the work of Fian and Linnes, where they're studying the Q fixed point, but they're not doing the Hamiltonian. But they're studying the Q fixed point equations for the non-abelian Seiberg-Witten equations, where you have one hypermultiplet in the fundamental.
And that to try to prove the formulas that come by comparing the UV to the IR theories.
Exactly. So, right. So it's an old idea of Pitt-Strigach and Turin. The original idea, well, I showed you that we had that whole discussion I had before about fixed points and the abelian and the instanton branch, that applies to any Seiberg-Witten, non-abelian Seiberg-Witten. Here we are. Any non-abelian Seiberg-Witten theory. And so that's exactly the idea. So the idea of Pitt-Strigach and Turin was, when m is 0, we have the instanton moduli space. But then there's this other set of fixed points. And so then we can hope that the moduli space is some kind of cobordism from instanton moduli space to the abelian Seiberg-Witten moduli space, and thereby explain the Witten conjecture. And they've essentially been successful. It took a lot of hard work, but they've essentially been successful in implementing that idea. We're looking at it slightly differently. We're integrating over the non-abelian instanton moduli space, and we're getting contributions from the two branches like that.
Are there any more questions? In that case, we'll thank Greg again, and we'll reconvene for a discussion in 10 minutes. If anyone wants to join the discussion and doesn't have the link, send me an email, and I'll send you the link.
Okay, see you in 10 minutes.
Thank you again, Greg.
Thank you.